So I'll jump in. I'll try to be quick. My name is Scott Pearse. I'm a software engineer up at NCAR, the National Center for Atmospheric Research, and I work on a project called Vapor, along with my teammates John Klein, Stanislaw Jarasinski, and Samuel Lee. This is going to be a quick introduction to Vapor, and I guess the big important question to answer first is, what is Vapor? It's a 3D visualization package, just like ParaView and Visit, but it's geared more towards scientific users, not as much as pure visualization experts. Like Visit and ParaView, it's open source, it's cross-platform, so you can get installers on Linux, CentOS and Ubuntu, OS X and Windows. And Vapor is a tool that's comprised of about 10 things that we call renderers. And I think ParaView calls these filters, and I think Visit calls them plots. And I feel like maybe we should change the name of what we call this thing that depicts our data into something more consistent, because I don't know, I love consistency, and I think it gets confusing if you have too much terminology to these things. Vapor's goal is to make visualization easy for geophysicists. And so we want to make the process of 3D visualization as easy as possible for the scientific users, so they can spend more time on their domain science. Our website is www.vapor.ucar.edu, and we have a group email address, vapor@ucar.edu, and you can also ask us questions at vapor.discourse.group. In this session, I'm going to go through the application overview, basically the workflow of how you create visualizations with Vapor. I'll talk about our supported data formats. I'll create and enable and configure a volume renderer, and I'll do a demonstration of pathline rendering for the first time. Pathline rendering, streamline rendering, and volume rendering are our flagship renderers. But pathline is the most complicated one, so I'm hoping to march through that one for the first time in a demonstration that's live. And then if there's more time, I can talk about other renderers, but I'll probably just hand it back over to Cyrus if there's extra time and no questions at the end. So you're all familiar with Visit and ParaView, and these are the heavy hitters in the scientific field of visualization. I don't think any two applications publish more scientific viz than these two guys, maybe Blender's up there too. But why is there room for a third 3D visualization application? And the reason I would argue is usability. This isn't meant as a slight to Visit or ParaView, but these are very complex user interfaces, and to a novice in the visualization field that's focused more on their science, this can be pretty intimidating, in my opinion, there's 1, 2, 3, 4 top-level menus, a left control bar, a right control bar, and it can be hard to find what you're looking for unless you know where it is already. So if we compare this to Vapor's user interface, I'll say that Vapor can't do everything that Visit and ParaView can do. We are dwarfed by the capabilities of Visit and ParaView, and I think myself and my team look up to those two applications kind of like we would a big brother or sister. We look up to Visit and ParaView because they are implementing the scientific requirements that we need to do next. But we need to do it next in a simple way that a novice to visualization can approach. So this is Vapor's general UI, and it's comprised of 3 main elements. Up on the top left, we have our instance table, where we can see the list of renderer instances we've created. And in this table, there's a new button where you can create a new instance, and then you can select which renderer you're looking at or setting parameters for in this table. So in section number 2 is our control panel, where those parameters are laid out. So right now in our instance table, we've selected our volume renderer, and we can see in box 2 the parameters that are generating the volume rendering in box number 3. And so more about section number 2 in a minute, but that's the primary group of widgets that will allow you to apply your parameters to the rendering. So the workflow in Vapor is to 1, load your data, 2, create your renderer instances, 3, configure them, and then finally take a picture of them in the control panel or the visualization window on the right. So assuming we've already loaded our data, the next step will be to click on this new button where we'll see this drop-down menu that lists all the different kinds of renderers that a user can create. you can double click on the volume renderer and the table will be populated over here on the top left. And you can turn them on and off by clicking on this checkbox that's to the right of every instance. So once you've created your renderers, you can select the parameters that you see in the control panel by clicking on the row of that renderer in the table. Now in this control panel, there are 4 tabs. 3 of them are the most important. There's the variables tab, the appearance tab, and the geometry tab. And these correspond to what we are looking at. That's the variables. Appearance pertains to how we're rendering it, how it appears. And geometry is where we're rendering it. So it's variables is what, appearance is how, geometry is where. Annotation is just a tab where you can turn on a color bar if you like. But variables, appearance, and geometry are the big 3 players. So in my variables tab, for my current volume renderer, I've selected the Q cloud variable, and I can alternatively select color map variables for things like if we have an ISO surface renderer, our variable could be pressure, and we could color map that pressure surface by a secondary variable, say humidity, if you're interested in things like dew point. Again, this is an application mainly geared towards atmospheric scientists, so that's a common use case. After variables tab, we have the appearance tab where we find our transfer function. It works in the same way that it does with a pair view and visit. It's just a probability density function of the values of your currently selected variable, and then you apply a opacity map with these control points up here, and then the color is applied to those data values beneath the histogram. There's also other parameters in the appearance tab depending on the renderer you're using. Like for our raycasting renderers, like the ISO surface and volume renderer, there's lighting parameters, different algorithms you can pick, but the transfer function is the big one that's common amongst all renderers. Every single renderer is going to have a transfer function in its appearance tab that will behave in the same way. So once I show you guys how to use a volume renderer, hopefully it'll be apparent how to use all the other renderers and apply color because it all works in the same kind of way. The geometry tab kind of selects where in space you're rendering to. And so if you see our X, Y, and Z extents are the full maximum, we have these double slider bars that let you constrain where you're rendering to. So if I go to my next slide, we can see we dragged our Z maximum down lower, and you can see we're kind of cutting off a cross section at the top. I think this is a Hurricane Katrina data set. So in this lesson, I'm just going to go through 3 renderers. I'm going to go through the image renderer, which is popular amongst atmospheric scientists because you typically, for those users, they want a map at the bottom of their rendering just to give some sense of where we are in space. So I'll click on the new button, our drop-down image, or our drop-down menu will come down, and I'll double-click on the image button. We'll also do a volume renderer. And finally, we'll do a flow renderer with path lines. Let's see if I can get that going smoothly. So yeah, let's just keep on chugging forward. Again, our website, I guess I'll go to it really quick, www.vapor.ucar.edu, and it looks something like this, where you can download Vapor, see a quick start guide, go to our documentation, look at the source code on GitHub, or then go to our discourse forum by clicking on Get Help. So if I click on Get Help, I think you can use an OAuth 2 token, so you can log in with Google or GitHub to our discourse forum. And then one thing I want to mention in our documentation, let me get rid of some of these tabs. In our documentation, if I go too fast here, every single aspect of Vapor is something that we're trying to demonstrate in a YouTube video. So if you go to our documentation website and click on using Vapor 3, and then click on the renderers, there's going to be a list of each renderer. And if you click on those, there's going to be a YouTube video demonstrating how they all work. Yeah, I feel like I was once told there's 3 ways to learn something. The first and easiest way is to ask someone. The second easiest way is to look it up. And the third easiest way is to invent the solution yourself. And I think these YouTube videos are the closest thing we can get to number 1 by actually, when you ask somebody how to do something, they show you how to do it. And these YouTube videos are doing the same thing. But if they fall short, the discourse forum under the Get Help menu is the way to go. And then we can answer your questions if the YouTube videos are insufficient. So then let's see, back to present. There, okay. So supported data formats. Vapor, we kind of cater to this data format. It's a NetCDF configuration that comes out of the WRF ARW model. Down here, you can see a simulation using WRF data. And this simulation calls from a model called the HER. If you've ever seen or I'm sure you guys all look at weather forecasts, but if you ever look up your weather forecast at NOAA.gov, it's coming from the HER model. It's HRRR, it stands for High Resolution Rapid Refresh. And it's high resolution because this model is run once every hour, 12 time steps into the future, and it's run at a 3-kilometer resolution. So it's high resolution in space, and it's rapidly refreshing every hour. This is where all of our weather forecasts come from. And it's based on the WRF model. So this is a smoke visualization. So this is showing near surface smoke. I don't know how smoke is going for everybody else in the conference right now, but here in Colorado, we were listed on Saturday as having the worst pollution of any city in the world in Denver. So NCAR has a growing interest, at least in this particular variable coming out of WRF. So that's kind of who we cater to the most. They're probably the most prevalent users of Vapor, the WRF users. We also cater to impasse users as much as we can. And this is a unstructured grid with varying refinement in space. And so you can have a high grid resolution in the area you're interested in and a low grid resolution in areas that you're not. And it prevents you from needing to do this technique called nesting, but I won't get into it. Here's a Vapor visualization of WRF using our new Osprey renderer. And this is a simulation of a, gosh, what do they call it? A aquaplanet. It's like Earth, but there's no land. I'm not sure what the applications are for it, but I think it's kind of a neat concept at least. Moving on, the broadest, well, maybe the second broadest data format we support is NetCDF data that is CF compliant. And here's kind of one of our more, I'm not sure what to call it, but this is a data set from a meteorologist named Lee Orff, and this was like one of the first F5 tornado simulations ever done, I think at not Northwestern, it's University of Chicago, no, University of Madison. So this is just NetCDF data that is CF compliant. And what does that mean? If we look over here at the bottom, whoops, at the bottom left, here's a very generic NetCDF data if you're familiar with it. We have a time dimension, a Z dimension, a Y dimension, an X dimension, and a temperature that is a function of those 4 dimensions. However, the problem is that we don't know where this grid exists in space. And so for that, we need coordinate variables like X of X. And this variable will define where each grid point exists along the X axis. Likewise for Y and Z and time. Time will tell us what axis it is, the time axis, the units, and we have axes designated to our coordinate variables because it's, even though it's named X, we don't know what axis it pertains to just based on its name. We need these attributes. And so there's tutorials on our website for if you have NetCDF data, how to use tools like Xarray or NCO to make those variables and coordinate variables compliant with the CF convention so you can get your data into Vapor. Lastly, we took Visit's lead and are supporting a new data format that is called the brick of values. It's just binary floating point data. And basically, your simulation will churn out a series of numbers, and then you need to write a BOV file where you specify a time for that file, the data file location, the size, the format, the variable name, the origin of your grid in space, and then finally the size of the brick in space. And lastly, the last data format I'll mention is called the VDC. It's called the Vapor Data Collection. And what this is you can take any of the aforementioned data files and convert it into the Vapor Data Collection so that you can look at your data at progressive levels of refinement. Vapor can apply a wavelet transform that can cull off certain values if you want to turn the fidelity down. So imagine you have a very large data set and your data is not rendering, it's impossible to explore because it's not interactive. What you can do is you can convert your data to VDC and explore it at low levels of fidelity, like what we see here on the top left or in the middle. And then once you've picked a color palette and an opacity set of values that sort of illuminate your observable you're going for, you can then crank the fidelity all the way up to the original fidelity of the original data. And then press play, collect your images overnight, come back, and it'll be all there in the morning. Even though you couldn't interact with it at the high resolution, you still could at a lower resolution. So those are my slides. I'm going to now crack open Vapor. And I think the first thing I said I was going to do was create an image renderer. So I have Vapor already installed. I don't know if you guys can see my taskbar at the bottom, but I just click on that V and then Vapor has popped up. We have this notice board that is now asking everyone to fill out this new feature survey. So we just released version 3.5 on Wednesday, last Wednesday, and we're looking for new requirements for 3.6. And so if you guys do get to install Vapor and give it a shot, if you could fill out this survey for any features that you would like to see, that's going to be a good chance for you to give us feedback on what we should be doing next. So anyways, I'm going to click on don't check for notices and start up and close that. And so we don't have any data imported right now, so everything is disabled. First thing I'm going to do to demonstrate my image renderer is I'll click on the File menu, go to Import, and I'll do WRF ARW. And WRF ARW is a good candidate for the image renderer because WRF files come with this metadata that's called a projection string, which tells us where we are in space on Earth and how our data is projected according to its map projection. So I'll click on Open, and then we see our domain. I can right-click my mouse to zoom out or in. I can left-click to rotate the scene, and then middle mouse button will do a transposition. The first thing I'm going to do is click on this new button, and now we see all of our renderers that are available. I said I was going to do image, so I'll double-click that, and there is my image renderer instance in my renderer table. I'll click the checkbox, and there we have our first image rendering, but it's still kind of hard to tell where we are. I mean, if you didn't know that this was Hurricane Katrina we were looking at, it'd be hard to know that this is Louisiana and so forth. So what I'm going to do, I'm in my variables tab by default. I can pick a height variable, so I can offset my image by height, but this is such a flat region of the Earth, it's not going to do anything. So if I click on HGT, yeah, you can't even tell that it's offset. Maybe you can see Appalachia just a little bit right there. You turn that off. You can see it goes back down. So if you were in a more mountainous region, the height offset variable is a lot more useful. But since this is so flat, I'm not going to worry about it. I'm going to skip appearance on the image renderer and just go to geometry. And this is, again, where we are rendering to. And there's two ways to control it. There's these sliders that only pertain to the region that is within the domain. The image renderer is unique in that you can right-click on these handlebars that show up when you're in the geometry tab. You can right-click and drag them out and extend the image renderer past the domain. It's the only one that can do that because you don't need data outside of the domain to draw the map upon. Let's see, I think I just wanted to demonstrate the image renderer because that's probably the first thing that all geophysical scientists go to. What I'm going to do now is I'm going to close this data set and I'm going to load the tornado data set. I'm going to click yes. And so once again, why don't I just maximize the window? There we go. I'll click on File to get my data in, Import, and my tornado data set is NetCDF CF compliant data. Click on that, and then navigate to my data window. Let's see, May control, is this it? Yes. So I'm going to click on all my NetCDF files, click on Open, and here we have my domain for my tornado. Next, I'll be doing a volume render. So I'll click on New. Here's my volume renderer. I will double click on that and enable it. And by default, we're looking at the variable DBZ, and that's simulated radar reflectivity. You can't really see the tornado very well, but maybe you can see it a little bit right in here. I think vorticity magnitude is probably going to tell us where the biggest vortex is. So I'm going to click vorticity magnitude, zoom out, and with our volume renderer, of course, by default, all data values are completely opaque. And so I need to turn some of them off or apply opacity to them so that we can see through our volume. So I'll go to my appearance tab. In my transfer function, I have these 4 control points by default. I will click on the leftmost control point and drag it all the way down. And I can, in real time, see the data values mask out as I change the opacity for them. And then here we see our big worm, the main core of the F5 tornado that's pulling in these smaller tornado trains as it marches forward. For my transfer function, I can pick different color palettes by clicking on this gear icon. I can pick different color interpolation methods. Let's see, I don't think I need to do that. What I'll do is I'll go to load built-in color map. And Vapor provides color maps in 3 different schemas. There's diverging color map, which is what we have here, blue, white, red, and this is a diverging color map because we have 2 main colors that meet at a, well, often people put a white point in the middle to distinguish those 2 ends of the spectrum. And these are good color maps if you have a modal distribution, like a witch hat with 2 tails. One tail would refer to the blue colors, the other tail would refer to the red. But since this is not a real, it's kind of like a more sequential, it's not a modal distribution, I'm going to load a built-in sequential color map. And I don't know, I always think that, this is black body, yeah, I'll do that one. This one always kind of looks cool. But I need to do some adjustments. Let's see. So to control the 2 endpoints of my transfer function, I have this slider down here, and I can take one of these and drag it. And you can see my histogram kind of growing because the transfer function is now only referring to the data range that I'm reducing right now. Let's see. And let's see, what I'm going to do is I'm going to reverse my color map. So I'm going to right click on my color bar and reverse it. So now my low values will be white and then transition down into black, like so. And then it's really just playing with it. I mean, as a scientist, you're looking for certain traits. And I'm not a severe weather scientist, I'm an engineer. So I'm not sure what Lee Orff would be looking for right here, but I think he likes to talk about these worms that kind of dance around this main vortex as time progresses. Let's see, do I have time to step forward? Do I play forward? I'm not going to risk it, but if I played forward in time with these VCR controls up here, where we can play backwards, play forwards, or do single time step forwards or backwards, you would see these worms kind of getting sucked into the main core of the tornado. But let's just pretend that I have a visualization that I'm happy with. The last step is to take a picture. And so I'll click on my capture menu up here at the top. And I can capture a single image or an image sequence. So since I'm afraid of capturing an image sequence because I'm not sure if like my computer's going to lock up, and that'd be bad for the demonstration. So I'm going to capture a single image. I'll select a ping. Vapor will beg for citation. And we'll call this test. And this will be in my home directory. Looks like I've done this before. Place. And then let's see. Test.png. There it is. So those are the basics of the volume renderer. Now, for example, if you were to create a different renderer, like the slice renderer, it's the same thing. So now I have 2 renderers in my instance table. I can click on volume and we have our previous settings, but if I click on slice, we have all new settings, probably looking at DBZ again. So if well, I won't bother picking a new variable and stepping through it. The point I want to make is that the workflow is the exact same thing for all the renderers. You have your variables, appearance, and geometry tab, and you turn things on in the same way in all cases. But that's less true. I'm going to disable that renderer. I'm just going to go ahead, now that I have it selected, I'm going to delete it. This is all less true for the flow renderer, which is our flagship renderer, but it's also the most complicated one. It diverges in the way it works compared to our other ones. So I'm going to demonstrate that by clicking on New, double clicking on Flow. And so here's our flow renderer. Then you can see we have a variables tab, but the variables are different. We're not just picking a single variable, like with our volume renderer, there's only one variable to pick. With our flow renderer, there are 3 fields, usually pertaining to the wind vectors on X, Y, and Z. By default, Vapor will pick the first variable that starts with U for the X field, Y for the V field, and W for the Z field. And you can do flow with your 3-dimensional variables or your 2-dimensional variables. I'm going to go with 3D for now. I'm not going to worry about color map variables, I think. So that's kind of the difference with the variables tab. The seeding tab defines where you're injecting your streamlines or path lines into this scene. And so there's 2 different kinds of flow in Vapor. There's streamlines and path lines. I'm going to turn my volume renderer off just to give a demonstration. Go back to my flow renderer, to my seeding tab, and let's just turn it on just to give a demonstration. So this is the default distribution of streamlines in our flow renderer. This is kind of hard to comprehend, but if we scroll down a little bit, we can see these seed distribution settings. And this is how we are injecting our seeds into the domain. We have 5 seeds on the x-axis, 5 seeds on the y-axis, 1 seed on the z. And so it's kind of hard to see. They're long. If I reduce my integration steps to maybe 10 integration steps, you can kind of see that distribution of 5 by 5 by 1 a little easier. When I'm in my seeding tab, these handlebars show up where I can control where that grid of seeds is being applied in my domain. So if I drag that all the way down, all the seeds are now at the bottom, and now they're all the way at the way bottom. Let's increase it a little bit. And so what I'm going to do, let's turn my volume renderer on. We know where our tornado is. It's this big vortex right there. So if I go to my flow tab, click on seeding, I can now narrow in where I put my seed points by right-clicking on these handles. I can distribute them right in the middle of the vortex. And then I'll turn the volume renderer off. And then there's my seed points, but I'm not advecting them very far as streamlines go, so I can increase my integration steps. And we can see the streamlines advect up into the mesocyclone. One thing I can also do that I'll mention real quick, I can go to my appearance tab, and there's some special appearance settings for our flow renderer. I can turn on 3D geometry, so we're actually looking at tubes. Like if I turn that off, you can see they're kind of flat lines, but I can turn them into tubes. And then there was one thing, radius scalar. I mean, you can make them as fat or skinny as you like. And then flow fade tails. This is kind of a trick. So we're looking at streamlines right now, which are time invariant. So at a single time step, we're just looking at where these, where the wind vector would go, and it's completely time invariant. There's no real advection going on. It's just like a big arrow pointing to where the wind field goes. But Vapor can let you kind of trick this renderer into looking like it's time variant by using this fade start sample. And so if I wanted to capture a movie of that, I could go to my capture menu and capture an image sequence of PNG files. And then for every time Vapor renders, we would capture a PNG file showing that rendering. But what I really wanted to get to, I have about 5 minutes left. I wanted to get to path lines. So in order to do that, I'll go to my seeding tab, and the flow type, I will select path lines, path line length. And again, this is kind of like the volume render. It's a little bit of a trial and error thing. The path line length will just show how long your particle is. And I should back up a little bit. Path lines are time variant pseudo particle data. It's like a Lagrangian simulation, Lagrangian particle simulation, except for there's no accounting for things like mass, magnetism, or other things that would cause particle interaction. This is like throwing a bunch of feathers into a tornado. If you ever saw Twister when they, they deposit all those sensors into the tornado, this is kind of what that is doing. So going down the list of parameters, I have my path line length. I'll arbitrarily call it 3 Well, it's really just because I was doing this morning. I remember that was a good value. The injection interval determines how often we're throwing these particles or feathers into the tornado. A value of 0 indicates we're just doing it at time step 0. But if I do this at an interval of 3, that means every 3 time steps, we're going to be hucking a 5 by 5 by 1 grid of particles into the region that we've specified with this red box. Vector field multiplier, this is one you usually don't have to worry about, but in this situation, Lee's data, the UV and W wind vectors are measured in meters per second, and his domain is in kilometers. And so we have to adjust the multiplier for our variables so that the domain and the variables are on the same scale. So I'll put that at 001, and then let's see, I will press play, see what happens. And then there they are, starting to advect. And this is one of those scenarios where VDC might be handy because you'll be able to rapidly explore the data at a compressed level. And then once you've found the spot where you want to inject the seeds, you can crank the fidelity up and then press play and let this run overnight to capture your images. So, gosh, I'm almost out of time. I just want to say thanks again, Cyrus, for letting me get my 2 cents in before I go. So I'm not sure if there's any questions I can address with the 4 minutes I have left. Let's see. More chat. All right, guys. Well, thank you for your time. And if there's any questions that I miss, the Discord group is vapor.discord.com, I think. So let me double check that. .group. So vapor.discourse.group, or email me and my team at myself at Pearse@ucar.edu or vapor@ucar.edu.